So we decided to do solar power. Yeah, my name's Cameron, and our group, we decided the most useful thing we could use this data for was to figure out some additional data using the given ranges, like how much land could be saved, what percent this could make up of the global power, and if all of these panels were upgraded to class 10, which right now is the highest end, at least according to the spreadsheet, how much energy could we expect from these things if we were to upgrade them? So that's what we did. We have some basic assumptions right here in the beginning. Then we move on to some outside source data, and this is the world production of energy from 2012 the world census. I actually have this right here. If you look down at energy, so the number of production is going to be 22.57 trillion. We're going to go over here, and that is the corresponding value. So that is our world production that we used to calculate all of this data. I'm sure it's a little bit off since it's somewhat far removed, so our program works better if this was the year 2012. So here we load in the data in the spreadsheet. We just load it all in, numbers, text, and raw. I think we only ended up using numbers because we decided the text and raw were a little bit too difficult to work with. So that's what this XLS read command does right here, is just took the data from my spreadsheet and loaded it in as a matrix that we could work with. I'll show you that in a second in the workspace once we boot this thing up. So actually, why don't we do that right now? Just get some values to work with. So here we have the min and max class ranges. I decided to set those by hand because since there were inequality values and ranges, the string was a bit complicated to work with, and Coda said it was fine, so I just went with that. It seemed like it would save a little bit of time. This extracts the class number. So the class numbers are here's our data set. And you'll see the class numbers are over here, right here, and they correspond each to an efficiency. And what we wanted to do, since these were a range, were to essentially replace the range with a medium value to kind of get a base efficiency for each of these classes. And I decided the best way to do that would be to average them all based on the class. So to replace the class with the average data that I pull from. So like class 1, then it goes to my little matrix I input by hand, class 1, and then I took the average value of that and then input it at that location. I'll show you how that worked logistically in a second. So that's what class number is. We just loaded in those numbers, and then the yearly power was the power right here. We took it in megawatt hours per year because it was the closest to the efficiency, and we needed both of those values here. So here we convert it. We decided to convert the production as opposed to the efficiency. It just seemed a little easier. So we converted over the production. Here we took the average, min, and max. So it's average class. I'll show you what that looks like. That's what I was talking about. So here's the average for each of those classes, as you can see. And then we converted it to megawatt hours as well. So this goes ahead and sums up all of that yearly power. TE break. Okay, so the for loop I had a lot of fun with. It was a fun little project to do. And essentially, it starts with a value, and this is the initial value of 1. and it increments from 1 by an integer value of 1 to the length of the class, which is a column vector. So it's going to run once for each instance of a value in the column vector. And then I made an efficiency vector. Originally I had this inside of here to where it just incremented and created, but MATLAB gave me a little heads up and it said, hey, if you create it outside, it's going to save your program a lot of time. And it actually did save me a noticeable amount of time. The program was taking a little bit longer than you saw even earlier to run, and I think it was mostly because of this for loop. After I kind of optimized a little bit, I'll talk a little bit more about how to optimize the program in a little bit. So that's what I did with efficiency, and I took every number, so 1, so then it would pull the class 1, and wait now. So yeah, it would pull the class at 1. So if it were the 98th instance of this loop running, it would return the number 2, and the number 2 would in turn be passed through average class, and then it would put in that 98th position 1.1871, which is the variable associated with the average. So that goes into efficiency, and it creates an efficiency vector. It looks something like this. I think it came out. I was very happy to see that it worked. So we have all of our values. So that was, I suppose, the biggest arc in the coding. After that, it gets a little easier. So the first problem we wanted to solve was to calculate the land required to house all of the solar energy. Because if we know the efficiency per meter squared and we know the yearly power, then it's pretty simple to just figure that out. So that was the first benchmark that we went through, and we did this by dividing the column vector containing all the powers by the country by the new vector that I made with all of our efficiencies. And this gave us a yield of land. I then summed up the land in this vector. At this point I encountered a slight error. This was probably the biggest error. So if we go look at our land total, you'll notice that this is a ridiculously large number, and this is easily 3 times the Earth's surface area, and there's no way we have that many solar panels, because due to the nature of solar panels, you can't stack them, so they all need their independent space. So this was a ridiculous number. We spent a lot of time going back through and trying to find an error in this math, and we couldn't. So that was a pretty big issue for us. So we ended up going to talk to Dr. Olsen and a few TAs and decided that we were going to treat this data set right here as if it was in kilowatt hours per year. Because there's just no hole in our math. I mean, feel free to look through it yourself, whoever's watching this video, whether you be students or teachers, because I'd really like to figure it out, but there hasn't seemed to be any holes in our math that we can find. So we changed this to kilowatt hours, and that's our second instance of code here. And I'll run this, and as you'll see, we'll get a different value for land total because it runs it a little differently. So it is the same value, but it is to a less degree due to the nature of conversions, and we actually removed our conversion factors. So after that, it's pretty simple, smooth sailing. We have the sum of the land, so we summed up all the land we needed. Okay, showed you that in the last one. Just to recap, and then calculated the power if they were all upgraded. So now that we had the land, we could take the efficiency of the class 10 and figure out what kind of power we could generate from that land. So that was pretty cool to be able to figure out something that wasn't given in the data set. And it was pretty easy, it didn't take too much coding. So MATLAB definitely made this problem a lot easier to solve and the data a lot easier to work with, because it was a huge data set and adding those by hand would have been a pain. Then we calculated the difference that could be achieved. So we took the current global solar power based on that Excel spreadsheet that we were given, and we subtracted that from the amount if they were all 10. Next, we wanted to see how much land could be saved if we wanted to create the same amount of energy as the lesser class solar panels were. So here we have that. We have the global power divided by the efficiency of class 10 solar panels, and then we subtracted that value from the total land whenever they were all different solar panels. The higher value for the efficiency of class 10 yielded a lower amount of land, so it was easy to subtract it. Inverse relationship there. And finally, we just took percentages using that website I showed you earlier and comparing it to the world production, world consumption, and global power, and seeing how much percent-wise could this account for if we were willing as a society, as a world, really, to invest our time and efforts into solar energy and upgrading the efficiency of these panels. So I'll just go ahead and wrap it up here by reading through this statement. According to our data, the world provides 9.75 times 10 to the 14th kilowatt hours of electricity through solar arrays every year. The solar cells take up 5.87 times 10 to the 5th square kilometers worldwide. If all of these solar cells were converted to class 10, the electrical output would be 1.65 times 10 to the 15th kilowatt hours per year, 170.32% of the original output. Using only class 10 solar cells, only 3.44 times 10 to the 5th square kilometers of land would be needed, a whole 2.42 times 10 to the 11th square kilometers less land than is used now for the same amount of energy. That is a lot of land saved. So I was pretty happy with the result. Unfortunately, writing a MATLAB program is not going to convince anyone to go upgrade these solar panels, but it's pretty cool to see what the benefits would be if this was more of an importance today. Some of the limitations of this, I think that I don't know, we had a lot of that issue with our data set, so that makes me feel like this overall could be kind of unreliable. I personally don't necessarily trust the data that much because of that issue we had. You know, it could just be a typo, but it doesn't seem super likely to me. The math is right, so maybe finding a more reliable source would improve the efficiency and accuracy of it. And then secondly, I think grabbing the world power consumption from 2012. Unfortunately, it's hard to find that sort of stuff out whenever there's not a census, because that's when we get most of these facts and information on the world is during the years of the census. So short of trying to calculate it independently, there's not much that can be done about that. So it does have its limitations, and if it was to be used in a professional setting, I think it would need to have those things tweaked and worked out, bug fixed, and kind of made precise. But I think you'd also have the support of like a big company behind you to help with some of those resource concerns.